I'm going to spend about another day talking about the rest of section 2.5, more on fundamental subspaces. Um, Please read, there's a couple of pages on something called the superposition principle, pages 111 to 113, which are a bit of a digression. So I'm going to ask you to read those on your own. It's pretty straightforward. Please ask me about them in class if you have any questions. And I'm going to go on to talk about uh, some other stuff about the adjoint and so on. So let me remind you where we were. So we were talking about the situation where you have A is an m by n matrix, and we think of A as being a function that takes Rn to Rm. And I've talked about the subspace here, which is the kernel of A. And I've also talked about the subspace here, which is the range of A. And I also mentioned the important fact that the dimension of the range of A is exactly the rank. Okay, so now we're going to play an interesting game here, which is to look at the transpose matrix. So I've mentioned before a few times, A transpose is the flipped matrix, which is to say it's an n by m matrix, where you just take this matrix and you flip it around the diagonal and you switch m and n. And what that does is it gives you a map going the other way. That is to say, the transpose is a map in this direction. And now you can play the same game about the kernel and the range of the transpose. So you can look at the kernel, let me move, the kernel of the transpose is now on this side, whereas the range of the transpose is on this side. And there are some subtle and important relationships between these various subspaces, which I'm going to talk a little bit about now, and then we'll come up actually in a later chapter. So before I dive in, let's do just a really quick example just to illustrate the ideas in a couple of points. So suppose that the matrix was 1, 1, 1, 2, 3, 4. That's A. So this, remember, is a map from R, from R3 to R2. And the kernel is a subspace of R3, and the range is a subspace over here. And what do we know about those? Well, if you put this matrix into row echelon form, you get 1, 1, 1, 0, 1, 2. And so it has 2 pivots and 1 free variable. And that says that the dimension of the kernel is equal to 1. And the range, what's the range? The range is the dimension of the span of the columns. And clearly, if you look at these columns, these first two columns, for example, are linearly independent. So the two of them span all of R2, so the dimension of the range is equal to 2. But now let's look at the transpose. A transpose. So that's the matrix 1, 1, 1, 2, 3, 4. And this is a map from R2 to R3. And what's the dimension of the kernel? Well, let's see, if you put this in row echelon form, it looks like it's going to have two pivots and no free variables. Whereas over here, if you look at the span of the columns, it's clearly 2. So the dimension of the range is equal to 2. All right. Well, the first thing to notice is that these subspaces don't really have anything to do with each other. So the way I've drawn it here, I have my R3 here and my R3 here. And so these two subspaces, this one, the kernel of A, and this one, the range, I should have said this is the range of A transpose, and this is the kernel of A. One of them is one-dimensional, one of them is two-dimensional. And they don't really have much to do with each other. They're not equal, obviously, they're not the same dimension, but, and as another point, you might think that the dimension of this range and the dimension of this range both being 2, does that mean anything? Well, these are subspaces of different things. This is a subspace of R3, this is a subspace of R2, and there's not really any significance. That's just kind of an accident. And the two spaces that we should be comparing are these two. And here we have a two-dimensional subspace. Here we have a zero-dimensional subspace. What's going on? And if you think about if you just think about the equations, if you write out the equations for these various things, this has to do with the equations x plus y plus z is equal to 0, the kernel, for example, and 2x plus 3y plus 4z is equal to 0. Whereas this corresponds to the equations u plus 2v equals 0 and u plus 3v equals 0 and u plus 4v equals 0. And they're just totally different. And as I said in class the other day, if you're talking about this space, when you do row echelon form here, this has to do with the rows. Whereas when you do row echelon form here, well, it's the rows here also, of course, but that corresponds to the columns here. And so it's complicated. But there are some relationships which are important and don't jump right out at you, so let's look at that. So before I go on, let me just introduce a couple of new, a little terminology. So if we have this, this matrix A, which is m by n, and it's a map from Rn to Rm, and going the other way, as I said, we have the matrix A transpose, which goes the other way. And we have the kernel of A, and over here I'm going to label it the co-kernel of A. And the co-kernel of A is just another word for the kernel of the transpose. And similarly, over here we had the range of A. And over here, I'm going to label the corresponding thing the co-range of A, which is just another word for the range of the transpose. Okay, so you use the word co, or the prefix co, to specify that you're talking about the corresponding object for the transpose. The co-kernel of A is the kernel of the transpose. The co-range of A is the range of the transpose. Okay. So notice that the range of A is the span of the columns. And so what's the co-range of A? It's the span, well, it's the columns of the transpose, but that's just the same thing as the rows of A. So, and one final thing is that the dimension of this thing is the rank of A. Now, of course, just looking at this picture, the range of A and the co-range of A live in different spaces. So these two spaces don't have anything directly to do with each other, but a basic fact is that they have the same dimension. The fact is that the rank of A is equal to the rank of A transpose. Otherwise said, the dimension of the range of A is the dimension of the co-range of A. So that is to say, these two spaces, the range and the co-range, they have the same dimension. Okay. Now, especially if this was a square matrix, so M was equal to N, you might be tempted to think that those two spaces are equal, but they're definitely not. The only property they have is they have the same dimension. And I'll write this one third equivalent version, which is in some sense the nicest. It says that the dimension, the range, remember, is the span of the columns. So that's called the column space of A, is equal to the dimension of the row space of A. So let me separate this out. So this last thing is just the statement about A. You take the rows, and that spans some space, and you take the columns, and that spans some space. Those two spaces have the same dimension. Okay, so I'd like to explain why this is true. Um, and the version I'm going to use is the very last one. I'd like to explain why the dimension of the column space is equal to the dimension of this row space. Well, I'd like to illustrate this with a really simple example. Suppose that my matrix was 1, 2, 3, followed by 1, 2, 3. Kind of a silly example, but what's the row space? Well, when you go to calculate the row space, you can do row and column operations. Because adding a multiple of a row to another row clearly doesn't change the row space. And so that says that the row space of A is exactly the same thing as the row space of U, where this is the row echelon form, upper triangular form that you put it in using row echelon. And if this is my matrix A, its row echelon form is obviously 1, 2, 3, 0, 0, 0. And the dimension of this row space is equal to 1. Now, what about the column space? It's definitely false, or let's just say it's definitely, whoops, here we go. It's definitely not true that the column space of A is equal to the column space of U. And that's just clear by looking at this example, because the column space of A is just the span of the single vector 1, 1. It's one-dimensional. It's got this vector in it. It also has this vector and that vector, but those are multiples of it. Whereas the column space of U is the span of the vector 1, 0. And those two spaces are definitely not the same. However, they do have the same dimension. That's the key point. Even though these spaces are not the same, these two here have the same dimension. And the reason is that the way you figure out the dimension of the column space is you look for whatever linear relations there are between the columns. And what's true here is that 2 times the first column is equal to the second. And of course, 3 times the first is equal to the third. And that's still true here. Even though you've changed the vectors, the key point is that these columns have exactly the same linear relations. So that is to say, however many linearly independent vectors you have over here, you have exactly the same number over here, and the same and then the other vectors have the same relationships to them. So um, that's the key fact. And now, what is the dimension of this the column space? Well, it's the number of pivots again. These both have the same dimension, and it's just the number of pivots. And so remember, the dimension of the row space was given by the number of pivots, because that's the number of rows of the row echelon form. That's this one row. And when you're looking at the columns, you count the number of pivots to get the dimension of the column space. And so those two numbers are the same. Okay, so that's the key fact that's behind all of this. Okay, there's one more main result from this chapter along these lines, which I'll explain now. So, as always, we have our m by n matrix, which we're reminding ourselves we're always going to remember is a map from Rn to Rm. And the result is the following. The dimension of the kernel of A plus the dimension of the range of A is equal to n. So this is quite a useful fact. So I was talking last time about the co-range and the co-kernel and so on, and that's going to come in, but forget about that for now. It's just a fact about A, the kernel and the range. The sum of the dimensions is equal to n. And why? Why is that? So let's see. So we take our matrix A and we reduce it using row echelon form to some matrix U. And remember, the main thing to keep in mind is that doing row operations is always okay when you're talking about vectors in Rn. That is to say, on this term, this has to do with rows. The range is over in Rn. This has to do with columns. So as far as the rows go, you're fine. And in fact, the kernel of A is really exactly the same thing as the kernel of U. Doing row operations doesn't change that. And so let's say we have it in row echelon form. So let's say we have some entry here, A1, and then who knows what, and then maybe A2, and then who knows what, and then some zeros, and A3, and so on. And then, of course, at the end, you can have a row of zeros. And you circle the pivots as usual. Okay, and let's remember what information can we get from this. So remember the number of free variables. The free variables are the ones without pivots. And so the dimension of the kernel of A is the number of free variables, which is n minus the number of pivots. Right? The number of columns here is n, and the free variables are the ones without pivots. So that tells us what this side is. It's n minus the number of pivots. And now, what do you know about the dimension of the range? Well, going to row echelon form is, as I said, that messes everything up having to do with the range. But the key point is that the dimension of the range of A is, by the preceding result, the same thing as the dimension of the corange of A, and the dimension of the corange is is the dimension of the row space of A. You take the rows of A, and you see that what's the dimension of the space they span, and the dimension of the row space of A is what? Well, let's see. The non-zero rows are the ones with pivots, and it's easy to see they're linearly independent. So it's the number of pivots. And there you go. If you add these two numbers up, you get n. So the dimension of the kernel, maybe I'll write it up here. This is n minus the number of pivots. Excuse me, that's an n. And this term here is the number of pivots. And those two numbers add up to n. So that's why this is true. Put all of this information into a diagram as follows. So A is our m by n matrix, and we have this map from Rn to Rm, and over here we have the kernel of A, and we also have the corange of A, which is to say that's the same as the range of A transpose. And then back over here, we have the range of A, and we have the co-kernel of A. And I'll remind you that this is the kernel of A transpose. Okay, and what are the dimensions of these things? The first thing that we know, first crucial fact, is that these two numbers, the corange and the range, are equal. So when I say equal, I mean having the same dimension. And the other thing we know is that these two numbers add up to n, and these two numbers add up to m. So this is the theorem that I just proved. The dimension of the kernel of A plus the dimension of the range of A, those two numbers add up to n. And, well, those replace the range, dimension of the range with the dimension of the corange, you get that these two numbers add up to n. And if you just apply the same thing to the transpose, you get that these two numbers add up to m. And I find this quite a useful diagram. It's nice when you have two subspaces where the sum of their dimensions adds up to exactly the dimension of the vector space. So it's easy to remember these relationships. If you know the kernel of A, it's easy to remember that this other vector space must have dimension n minus the dimension of the kernel of A. All right, that's quite a bit for today. That's a good place to stop, and I'll do some examples in class tomorrow.